So let's try to find the time complexity of merge sort. Suppose we have a set of size 2k. Our metacode is to split the set into two sets of size k, sort the two sets, then merge the two sets. We determined that merging two sets of size k required 2k minus 1 steps. So suppose that sorting a set of size k requires t of k steps. Then sorting a set of size 2k will require. While we could use the recurrence relation, it's convenient to write it as a function of n. So if n equals 2k, then k equals n halves, and our recurrence relation becomes. Now if we compute the base case, we can use it to find all other values. For example, to sort a set with n equals 2 elements requires t of 2 equals 1 comparisons. Our recurrence gives us t of 4. T of 8 will be t of 16 and t of 32. What we want is a closed form expression for t of n that allows us to compute it without requiring the preceding values. However, we might not need the exact formula. If our goal is to compare algorithms, it will be sufficient to find f of n where t of n is big O of f. So we can assume an ansatz, a form of f of n that might be suitable. Recursive algorithms and recurrent sequences lend themselves naturally to induction proofs, with a slight twist. Note that our recurrence relation is, so what we really want to do is prove the statement is true for some starting value, and prove that if the statement is true for n equals k halves, it will also be true for n equals k. Also in a standard induction proof, we try to prove the base case first. But in this case, we're looking for a bound on t of n, so we might not know the exact function, and so we can't actually prove the base case. So let's start by trying to prove the induction step using our ansatz. And the reason we do this is that if we can't, we'll need to change the ansatz. So our naive sorting algorithm is big O of n squared, so we might begin by assuming that t of n is also big O of n squared. If we succeed, this means that merge sort is no worse than naive sort. So if t of n is big O of n squared, then there's some c where for sufficiently large n, t of n is less than or equal to cn squared. Equivalently, since n is just the argument, that means that t of n halves will be less than or equal to for sufficiently large values of n. So substituting that back into our recurrence relation, we get. Now, we'd like to prove that this is ultimately less than or equal to cn squared. And so what that means is that as long as we increase the right-hand side at each step, then we can maintain the inequality. So we can increase it by not subtracting 1, and we can increase it by making n larger. How about by multiplying it by a factor of cn halves, because again, n is sufficiently large, which gives us, and this proves our induction step. So this proves that merge sort is at least as good as naive sort. But might it be better? Well, let's see if we can find t of n in a smaller big O. Since t of n is definitely in big O of n squared, let's see if we can lower the exponent. Suppose t of n is in big O of nk, where k is something between 1 and 2. And as before, we have t of n halves is, and substituting this into our expression, we get. Now, we know that t of n is going to be less than or equal to cn squared. So we know that we can get to this end where it's less than or equal to cn to the k. So let's go ahead and write that as our destination. Since we want to show that t of n is less than or equal to cn to the k, we want to compare cn to the k to something smaller. That way we can interpose it between our starting and ending points. If k is greater than 1, then we have, where our choice of the left-hand side here is because that expression shows up in our inequality, And in fact, if we multiply by n to the power k, we have Cn to the k. We have one term of our inequality. And this allows us to replace this term with something larger and maintain our inequality. But this will only allow us to get t of n less than or equal to Cn to the k plus n, and we can't get rid of the n. It's added, so we can't just drop it off. At this point, we'll introduce something that's really remarkable. In a surprising number of problems, aesthetics matters. In some sense, our original inequality here is a bit ugly because it has this power k minus 1. So what if we use instead this comparison, where our exponent is much nicer looking? So again, that allows us to have this, and this allows us to replace c over 2 to the k and k with c n to the k. This is useful because we can, at this point, replace that n with something definitely bigger. So we can continue our inequality and combine less than or equal to Cn to the k. So this suggests that merged sort is big O of n to the k for some k between 1 and 2. At this point, we'll take an intuitive leap. Remember, the order of n log n is greater than the order of n, but less than the order of n to the k for any k greater than 1. So might t of n be big O of n log n? So suppose it is. Then t of n is less than or equal to c n log n, dropping that into our recurrence relation, and doing some algebra. And we can not subtract to get a larger value. We can make n larger by multiplying it by c, then factor, and we have a problem because we can't get rid of the n. Now we could abandon our ansatz, but remember big O of n log n is the same as big O of n log n plus n, which suggests we might still be able to prove Tn is less than or equal to Cn log n if we take a closer look at our steps. Now if T of n is less than or equal to Cn log n, then T of n is less than or equal to C prime n log n for any larger C prime. So we can assume that C is as large as we need it to be. And note that if C is large enough, then n is less than or equal to Cn log 2, which means that Cn log 2 minus n is a non-negative number. So we can rewrite our inequality as, and since we're subtracting non-negative numbers, if we don't subtract them, we'll make our quantity larger. So that means we can rewrite our subtraction, which proves the induction step. Note we still need to prove the base step, and so we note that if c equals 5, t of 32, that's 129, is in fact smaller than 5 times 32 log 32. Note that we also required that n was less than or equal to Cn log 2, which will be true if c equals 5, n equals 32. And so that tells us T of n is big O of n log n. Now, while we already knew this because earlier we determined that T of n was actually n log n to base 2 plus n minus 1, this suggests a way to find the big O of an algorithm without having to determine the exact number of steps. We'll take a closer look at that next.